am delighted to introduce our first spring webinar speaker, Mahshid Ahmadi from the University of Tennessee, Knoxville. There we go. I almost said the wrong institution. And the talk will be on towards self-driving labs, automation and AI for the next era of materials innovation. So please, Professor Ahmadi, take it away whenever you are.
Yeah, thank you so much for the invitation. Really pleasure. I actually met Joanne a couple of months ago when she was visiting our university to give a seminar, and I invited her to my lab, and I'm glad she was interested. Thank you so much. Well, today I know that these days a lot of people are talking about AI and automation. I am lucky to share my journey with you guys since 2019. I started the journey on automating my lab. At that time, the interest was not as high as these days, but I'm glad that we kind of survive and we continue. And my apologies, I'm actually using two monitor. If you see me here and there, that's the reason. All right. So one thing that I would like to kind of say that it looks like material science, we always say material science cannot change overnight, right? But from the trial and error of the 20th century, all the way to the computation era of the 2000, I would say our approach in material science has really evolved, but really never rapidly and radically as they are these days through the experimental acceleration and the use of AI and automation. So what happens now comes very close to really material science is changing overnight. So little bit on the basically pivot from pure theory in materials discovery to experiment. We all are familiar that in 2011 there was a White House Materials Genome Initiative, MGI, which has the basically bold goal of cutting in half the time from the discovery to the deployment. This effort, the MGI actually seeded a wave of platform that they most of them initially emphasized the theory and computation. From 2000, basically, let me use my laser pointer. From 2013 and 2017, we saw a first generation of materials AI startup that they appeared. Many of you may be familiar with these companies. The focus of all of them was on basically data infrastructure and predictive model. Most of these efforts were still really decoupled from experiment. The pivot actually started really in 2023. At least I would say 4 years after I started my lab, that the labs like Berkeley A Lab and Carnegie Mellon Cloud Lab, they started to bringing AI directly to the experimentation and to the experimental loop. Growth has been really explosive. As you are familiar with that, in only 2024, we saw the Microsoft and the PNNL basically announced the AI Discover Battery Material Project. We see the Lila Scientific basically invested over 500 million for the experimentation and AI. Then, maybe you guys are familiar with recent investment by, former CEO of the Amazon and really other, I think that's over 6 billion or something around that, if I'm not wrong. So anyway, what I would say is what we are seeing is basically the shift from the theory-centric materials genome era to a new experimental AI era, where we are expecting that the autonomy, AI, and the venture scale investment are finally merging together to deliver a more tangible discovery and accelerate materials innovation. So, we all talk about the materials uh, discovery, right? But we should also remember the history. Um, there's this book which discussed the historical awareness and the rational thinking in guiding human behavior and avoiding past mistake. So I would love to always kind of bring that those who cannot remember the past are condemned to repeat it. So by saying that, I want to basically drag your attention to the history of the high throughput experimentation and combinatorial synthesis. So the history of the combinatorial synthesis basically and high throughput materials discovery, it has a lot of, we call it winter and summer. It began actually in late 60s and 70s when we had these diffusion couples and thin film spread libraries, which allowed the rapid mapping of compositional space of alloys, semiconductors, and even superconductors. That momentum was actually kind of cooled down. We call it the first winter in 80s and 90s. And the main reason for that was basically the automation really didn't exist. The data infrastructure almost non-existent, and the characterization was really slow at that time. And then we had the next basically recovery in 1995 to 2003. Professor Takeuchi in Maryland, basically, there was a wave of thin film libraries, combinatorial libraries that he kind of talked about it and was doing it. And there was even some companies like Stymex, they were saying the real value that this kind of combinatorial library can bring to the basically industry. And however, there was another winter of this combinatorial library, which was between 2004 and 2018, when we have this MGI, Materials Genome Initiative, because most of the focus of federal agencies and also the startup company was on, high throughput computation and data infrastructure and so on and so forth. And however, today I would say, again, we have luckily the current summer, which started lately with autonomy, AI, and machine learning. This is actually the picture of the combinatorial library of the halide perovskite that my lab generated since 2019. And right now, the high throughput experimentation is back to the forefront. Basically, this time is a part of the closed loop intelligent discovery ecosystem. So when we say acceleration, so what does acceleration of materials discovery really mean, right? So we all are talking about that. We want to close the loop from the synthesis to the characterization and updating the model, right? So like basically this loop that you can see here, but there is a big challenge here. The challenge, though, is the characterization. Characterization, as we all know, is bounded to the physics, right? There are hard physical limits to what, where, when, and how fast we can measure, right? You can measure only certain properties with really certain probes, right? X-ray diffraction can only measure the structural properties. It cannot measure everything that we want, right? So to really break through for the materials discovery, for the acceleration in materials discovery, we need to be basically smarter in the exploration strategy. Even now we even need a new paradigm of the measurements. We don't need a bigger microscope. We already kind of at the really high tech of all the instrument, right? The other thing that we do in today experimental workflow is most of our workflow is based on myopic optimization. What I mean by the myopic optimization is our decision making is basically maximizes short-term improvement rather than basically focusing on the long-term exploration or the global structure of the design space, right? We don't take full advantage of the proxy measurements. Right, we still rely on the expensive gold standard measurements. And in this presentation, I want to show you that this is one of the really main elements that we used in our lab for accelerating the materials discovery, how we are taking advantage of the proxy measurement. For example, in my lab, luckily, we can get lots of information from the photoluminescence, from optical measurements, before we start doing really expensive measurements such as, microscopy or X-ray. And then what today experiment requires is basically the well-defined optimization. That means we need clear definition of what success means for the AI to optimize effectively. And not only that, the big question is that what is the real economic value of our materials discovery? We just don't want to do faster science, but we want to also ensure what we discover it really matters in the world. So with all this introduction, I wanted to basically introduce the type of materials that my lab has been interested, and they are halide perovskite. You may be familiar with these materials or may not. So one of the beauty of these materials is that they have a really vast compositional space, but not only that, they are also having a really large variability in their structure. So basically, we have the 3D structure, which is the fully connected 3D network of corner sharing octahedra with some certain properties. We also have the two-dimensional, which are organic, basically molecules separating these octahedral layers. We have the one-dimensional, which is the chain of these basically octahedral, even the isolated octahedral, which make a zero-dimensional. And even more kind of exotic structure like corrugated 2D. And all these lower dimensional have different properties from the more conventional 3D perovskite structure. And in this presentation, I'm going to focus mostly on the 2D, basically halide perovskite structure. I know the focus of most of you, your research is on 2D materials, but this is a totally different 2D structure. So basically it's a combination of organic and inorganic materials. So why these materials matter is basically they have excellent or promising application for many optoelectronic properties. Most notable are the solar cell. In fact, I actually work on a startup company before I become a faculty on this perovskite solar cell. And they have application as photodetectors, LEDs, and even high radiation energy X-ray and gamma ray. And the reason for one of the basically beauty of them is basically they are made from solution, and that's why it makes them really cost effective. So, but speaking of the 2D perovskite, what is the challenge in this space? The challenge is basically we have a mixture of organic and inorganic, right? How can we really, and both of them have a wide range of the compositional space. How can we really explore the joint molecular and the inorganic compositional spaces, and how can we identify new physics in this space? So I'm just showing you a very small number of molecules that can be used as the cation or the spacer between these inorganic layers. As you can see, they have different shape, geometry, electronic state. They can even be monovalent or divalent, which are basically like oxide materials. They can be divided to the Radelson copper or the Jacobson type, basically divalent or monovalent organic spacers. But one thing is that the chemistry in these vast molecular space is inherently discrete rather than being continuous. So meaning like we cannot really predict the properties of one of them and extend it to the kind of similar molecule. So that make it really difficult for the exploration and discovery. So in 2018, so my lab started, the robotic synthesis of these materials. So I'm using the liquid handling robot to make them combinatorial library of them, either in solution form or as the printed film, which I show you in the previous slide. So I started from one basically liquid handling robot. Luckily extended to more robot. Currently, I have 3 liquid handling robot, and also I have a fully automated spin system. I want to kind of play the video. I have a fully automated spin coating bot, which is integrated with the in situ characterization. And this is here also again. Here you see the picture of the high throughput optical characterization that we have. And also on the top, we have the automated SPM spectroscopy. So basically, right now, we are fully autonomous in not only the synthesis, but also multiple basically characterization. So we started in 2019. We can experiment much faster, but the question is how we can plan the experiment, how we can be smarter and use the AI and the large language model into the equation. So initially, I want to show you what was my the workflow in my lab in the past few years, and then I will show you the most recent advancement. In this workflow, we started to actually use the large language model to extract the cause and effect from the literature. We started to using a large language model for the literature mining. So our purpose was to basically create a structured database from, because really the literature is so rich. Every year we create millions of the paper. Every day. Actually, there was an investigation by Future House that it not only in material science, I'm talking about all the science together. And the number is not exactly on top of my head. Maybe I'm saying wrong, but really in the number of like millions, either per year, per day, or whatever. But we are full with the number of knowledge and data that we generate, and that actually make the discovery slower rather than faster, because we have so much data, so much information, and if they are not structured, we cannot really take advantage of them. This is what we started to do it. So we want to use the LLM as part of the workflow to extract the knowledge graph meaning like try to connect different knowledge, and then and the dynamic schema, meaning every new knowledge from the experiment or the literature that comes, it can update our database. This can basically link the disparate data source, capture the cause and effect, and enable reasoning and discovery. Then we use some kind of the machine learning, like let's say the deep kernel learning, to select the promising materials. And I'm going to show you in an example how we use that. Then we use our automated basically synthesis and characterization to basically prepare these materials. And then we use our active learning and some of the machine learning model to get insight into the mechanism and also mechanism behind the phenomena we observe, and get the new insight and basically update our hypothesis. So I'm going to show you one example of how we used the large language model for the data mining. In this example, we did literature mining on only the experimental and basically literature, and trying to find what is the relationship between the structure and property of the organic molecules in the literature, right? So based on the so we wanted basically looking at favorite properties of the organic molecules, like their band gap, HOMO, LOMO, dipole moment, and so on and so forth. But we only found 100 spacers, 100 organic spacers have been experimentally synthesized and validated in the literature. So 100 database is really not enough for the machine learning to be trained. What we did, basically, we try to then use a bigger database of the organic molecules, which was not exactly related to the making perovskite, but had similar structure as the organic molecules that can make perovskite structure. So we looked into the database of the QM9. If you are familiar, this database has more than 100,000 of organic molecules and their properties. But among that 100,000, only 10,000 of molecules basically is related to the molecules that can be used for perovskite. So we basically augmented our data from the literature with these 10,000 data from the QM9 database. Then we used the machine learning model to pre-train that 10,000 data and use the training model on only 100 spacers that we found in the literature to understand their structure property relationship, but not to just passively do that, but also rank them for our synthesis. So in order to do that, we needed to actually, create a molecular graph, meaning like give information, create some information for each molecule. We did that using the RDKit and smart clustering. As I said, our goal was a promising organic spacer for perovskite, not to just predict their properties, but also rank them for our synthesis. So after that, we use the graph neural network to basically find the relationship between their structure and properties. And then we use the multitask Gaussian process to not only do the basically exploration, but also do the exploitation. By doing that, we did the dimensionality reduction, and this is the cluster k-means. Basically, we clustered the organic molecules into 6 different clusters. Every cluster have basically the commonly similar molecules. So, and then this is the representative of each cluster that I'm showing here. By doing this, we map basically the chemical space of all these 100 organic molecules from the literature and identified the promising candidate in order to use them for our synthesis, basically for our synthesis. So, but one really exciting element in our new journey, recently, is the introduction of basically agentic large language model. So instead of a single AI model passively kind of analyzing result or used for the literature mining, we try to design a system of different research agents that actively collaborate with each other. So we have the hypothesis agent, which is like the example that I showed you right now. It does the literature mining, but also do the Socratic reasoning and the tree of thought. So by doing Socratic reasoning, so we self-question basically the large language model to ensure the basically the depth of the knowledge, and there is a human AI interaction because we have tree of thought, meaning like after Socratic reasoning, we have the tree of basically different thought, and a human which is us, based on our knowledge and our novelty in the experimentation, we score those responses from the AI agent. We score from 1 to 3 based on our knowledge, and basically we go like a tree in order to create a hypothesis for our experimentation. And I'm going to show you a video of how this is really being done. And then we use the protocol design agent, which actually designed the experimental based on the hypothesis which was generated here. We do our synthesis by the robot that I show you, and then the characterization agent characterize mostly optical measurement in this case. And then we have the so-called peak fitting agent. It does the peak fitting. These are already basically formed. We have developed those of them, but the decision making and the orchestration agent, which is the voucher and basically correlate all of them, is still under development. In the next video, I'm going to show you, this is actually a video of how the AI hypothesis agent work. So I have some explanation because I understand that maybe there is no sound here. Okay, let me see if I can. It's going to take a minute, but I really want to show how this is really being made. And this is the hypothesis agent that is trying to generate a hypothesis when we want to choose an organic molecule to stabilize a 3D perovskite structure. So basically, we want to mix a 2D perovskite, which hypothesis a 2D perovskite that it can stabilize a 3D. And this basically agent provide the information, the hypothesis, to our synthesis or protocol agent. Then we make this, we do the synthesis. This is the high throughput optical characterization. And then, then we have the peak fitting agent. While the characterization is being done, the peak fitting agent does immediately the peak fitting, and this protocol is actually being done all fully autonomous. And as I said, our decision making is still under development, but and also the orchestration, how we can connect all of them together. But we are hoping this is actually the next step towards having a so-called self-driving lab. But I have to mention that we are really believing in human AI interaction, not only the AI part. And I don't want to go to the detail. This is the AI agent in action for the experimental planning. Let me also quickly play that. So after the hypothesis was formed, then the AI agent tried to do the experimental planning. So basically, how the liquid handling supposed to mix different ratio of the materials, as you can see here. Which instruments are available? The volume of solution dispensed into the volume, how much it should be dispensed. Again, based on the hypothesis report that we had from the previous agent. I'm not sure if you guys have the sound, but basically we are trying to explain every step in action that how, as you can see, basically this is different well of the well plate, and the agent is trying to guide us in each well what ratio of the 2D and 3D has should be mixed. Anyway, let's move to the next. So now in the next example, I actually would love to show some of the example of the real materials discovery that we had. In this example, I want to show you that, we hypothesize that if we have the steric frustration, which introduced by some of the organic spacer, this can lead to basically some asymmetric layer alignment. What does a steric hindrance means for those that they are not familiar with the organic chemistry? Is basically because of the geometry of the organic spacer, they can create some kind of physical blocking effect that reduce the chemical reaction or a structural basically interfere with some structural arrangement. So we hypothesize if we use this, a sterically hindering frustrated organic spacer, that may give us some kind of misalignment between the inorganic or the octahedral layer. But we didn't know how. That was the hypothesis. Then we actually selected, we actually selected these spacer molecules, which has two aromatic ring. This is a diphenyl propyl ammonium. We call it DPA. We selected that as it has a larger steric hindrance, and we mix these basically to the we mix this to the structure with different ratio of 3D perovskite. So usually in the perovskite community, people mix 2D perovskite to stabilize 3D perovskite, because some of the 3D perovskite have the problem with thermodynamic stability at room temperature, or they are not generally stable for long term operation of the devices. So that's the conventional. What we did here, basically, again, we mixed 2D and 3D perovskite. We realized that the pure 2D is not being formed as we expected because it has a larger steric hindrance. However, after minute incorporation of the 3D structure, it started to really crystallize, and you can see the color change. And when we looked at the absorption spectroscopy and the photoluminescence spectroscopy of these different compositions, we see a beautiful excitronic peak from the absorption and also the photoluminescence. But one thing that we noticed is that the photoluminescence of these 2D perovskite have significantly blue shifted as compared to the conventional 2D perovskite. And also the peak is asymmetric. That actually tells us something. And when we looked at their X-ray diffraction, we also realized that again, the 2D peaks started to emerge after 6% incorporation of the 3D. So that definitely tells us the 2D structure has been basically initiated by some incorporation of the 3D. Maybe this 3D structure mitigate the steric hindrance, but we didn't know actually how. But our high throughput combinatorial synthesis basically allow us to look for these changes. Next, we try to do the transmission electron microscopy. So we realize that unlike the rigid, basically epitaxial stack of these organic molecules between the octahedral in the classical 2D halide perovskite, these bulky DPA enable something that has never been seen before in the perovskite community, and that's the spontaneous twisted superlattice. Both the STEM and the DFT basically converge on 4 degree as the twisted angle, as the magic angle. And we believe that basically the steric and the thermodynamic favor these 4 degree. And this is really a unique self-assemble, bottom-up, basically growth of more superlattice, unlike top-down and very expensive, synthesis of the conventional 2D more superlattice structure. So basically this shows that how the hypothesis and high throughput synthesis and characterization resulted in a new discovery. So basically this is the first discovery of twisted Moyer structure into the halide perovskite. And as you can see is a self-assembly bottom-up basically synthesis rather than the intentional top-down. So one thing that we taught in terms of the mechanism is basically the structure of the DPA possibly offer these, flexible and disorder van der Waals surfaces. So in order to prove that, we actually looked at the DFT, because DFT always help us to understand the physics better or chemistry better, but we are much faster than theory. So we use usually theory for understanding the materials. We did almost high throughput kind of DFT, different coverage of DPA. And when we measured the binding energy, again, based on the binding energy calculation, we realized that the pure 2D cannot be formed because of the steric hindrance. However, when we basically increase, when we have the 3D structure, it actually stabilizes the 2D structure. However, that actually affect on the lead iodide lead angle. We have more distorted structure, and we have the octahedral tilting, which affect on the electronic properties. And in fact, that significant PL blue shift that we realize and the asymmetric tilt, asymmetric peak is because of these octahedral tilting. And when we did the density of a state calculation, we see that the band gap is actually increased by 0.4 electron volt as compared to the conventional 2D perovskite. And then again, in order to make sure that this is specific to the DPA molecules, we try 4 other different organic spacers with large steric hindrance, but none of them really resulted even in the crystallization or the Moyer structure. And that actually shows that the DPA, only DPA work, again, because of the specific geometry of these organic molecules, that it is rigid, and at the same time, these basically dangling group for the spacer allows the connectivity of the organic to the inorganic molecules and mitigate the steric hindrance. So that actually shows the uniqueness of the phenomenon. In the next example, this is also a very recent work that we use multiple characterization tool in our acceleration and automation to find a suitable material for solar cell devices. So first, use our autonomous platform, the SpinBot platform with in situ characterization, because the literature tells us that these different organic molecules, when they are being used with the 3D structure, it actually can result in high performance solar cell structure. When we actually looked at in situ luminescence properties, we realized that one of them have a fast characterization and one of them has the slow crystallization behavior. And we thought, what if we combine these two spacer and make a ternary composition of the two spacer and a 3D perovskite to control the characterization. So this is the workflow to identify the target phases that we used. So basically, in this workflow, which we use for the materials exploration, first in situ PL, basically select suitable 3D to 2D organic spacers. And after that, our high throughput synthesis and high throughput photoluminescence generate the optical spectra. And then we use the gated Gaussian processing model to propose the next composition by evaluating photoluminescence peak position for the band gap and also the intensity of photoluminescence for the stability. And then after that, so basically our next characterization come into the loop, which is the X-ray. We use X-ray for structural validation and basically convert the X-ray similarity into a structural target phase. And with that, we are having multi basically characterization feedback to converge to enable us to find the most stable and pure phase of the 3D structure for solar cell application. I'm going to show you. So basically, after doing the in situ photoluminescence in a fully autonomous way, then we did the high throughput combinatorial library of, this is the basically ternary phase diagram. And 96 of them has been synthesized. Then we measure the photoluminescence. Then the resulting spectra are analyzed by our AI agent for peak fitting to track the emission properties, identify the stable phases, and then the GPBO, Gaussian process Bayesian optimization, propose next composition by optimizing two PL parameters, their intensity and also the peak position. For the phase stability. And so basically, this is how our active learning work. By doing that, we did 6 iteration, and then the 6 iteration finally converged in 2 area of the phase diagram. Basically, these 2 area, it gives us the most stable target phases, right? But then we used, so basically, this actually shows with high, with low uncertainty. So in this example, we also bring the our uncertainty into our taken into account. And then so basically in these 2 regions, the compositions that we identify, then we do the structural characterization, the structural similarity score, further narrow down the search into only 3 compositions with the highest crystallographic match to the target phases. And in fact, I didn't show the properties here, but we made a solar cell devices out of these three composition, which actually show, relatively high performance as compared to, pure 3D phases. How much more time I have? So these are also some of the example. I quickly want to go maybe just 5 more minutes.
Yep,
These are
5
some
more
of the
minutes is perfect.
Yeah. Thank you. So these are some of the example of early work that we have. We actually use the high throughput synthesis and characterization to understand the early stage phase growth behavior in quasi 2D perovskite. So basically, our intent is not to only do the optimization, but understand the mechanism behind it. We don't want to use the AI only to optimize, because many people do that, but we want to also understand the mechanism. We want to visualize, for example, here the phase changes in our complicated system, and also build the thermodynamic model as we can see here. Sorry, I think I talked too much, so I am not able to show all the slide, but here we also did the high throughput grazing incident wide angle scattering, X-ray scattering in collaboration with Brookhaven National Lab. I guess I think that we are one of the first who has done that. We did it in 3 different incident angle to see how these materials are actually growing in the along the thickness of the film. And again, we use our automated peak fitting, which makes really the analysis of these complicated X-ray peak very fast. Basically, 250 peak can be analyzed in 15 minutes, every 95 in 5 minutes. And this is how we map the structural properties as a function of basically the composition. And not only that, we always benchmark. We always benchmark our high throughput synthesis on a printed, basically a smaller spot with the conventional method for making solar cell, which is the spin coating. So consistent PL trend again has been observed here. And this is another example that we actually use our high throughput experimentation to understand the basically broad band emission in the mixture of lead and tin to the perovskite. Again, since I don't have time, I just want to show you how we could beautifully basically map the whole compositional space to understand that what is the origin of this broadband emission in the mixed 2D and 3D perovskite, which is always depend on the different composition. And this is really not possible if we do not make the whole library of the materials. And again, to summarize, experimental acceleration, I hope I convinced that its theory is essential to narrow down and find the potential molecular or the literature, but we need the experimental validation, and through the automation we can do that in a faster and more precise way. We always try to be hypothesis driven. The discovery is hypothesis driven, and hypothesis formation can be done nowadays by using the AI for predictive basically uncertainties, and how the hypothesis can be validated through the experimentation. And we need to learn how to construct the iterative cycle of hypothesis making and the high throughput synthesis and characterization, and sometimes validated by the theory model. Well, looking forward to future when we can really combine all these in a seamless workflow. And at the end, this is actually not exactly what I do, but is the work of all the student and postdoc, past and present, and my collaborator. Every year I have visiting a scholar from different parts of the world coming to learn to use the AI and automation for materials discovery, especially in the field of halide perovskite. And happy to answer any question.
Thank you so much. We have time for a few questions. So if people online want to ask questions, you can raise your hand, unmute yourself. I'll put it in the chat, and I'll let Kelsey manage the questions in person.
Any questions from the room?
I know it's very different from the science you guys are doing, but I just thought that it could be really like exciting how things are changing, right?
Yeah, any in-person questions there, Kelsey? I can't see anything from here.
Yeah, Anthony has one.
Yeah, I guess, as you try to tie all of this together, you said the orchestrator kind of hasn't been built yet. Like, what are the problems that you run into when you try to tie these agents together? What have been the most difficult parts of building all this system that you have now?
Closing the loop, meaning like how we want to modify the hypothesis. It could be one of them. It is one of the most challenging because the protocol designer, is how we design the experiment. That's not a big problem for us in our field, in how we synthesize the material. But how to really update the hypothesis is still, I would say, one of the most important.
So as you get results back, and then you have to go back.
Yes. Yeah. We're developing it not because it's challenging, because it takes some time, and this is a new development in our lab. But I was really excited to show you guys because a lot of people are talking about it, but we have been really able to execute it to our automation in synthesis and characterization, as you saw in the video that my student made from her desktop, her monitor.
Yeah, very cool. Thank you.
Done.
Go ahead, John.
Hi, Mahshid. Thank you so much for giving this talk. This was really interesting. And I know there are a lot of people in the audience who are interested in trying to implement something like this for our thin film deposition tools. So this is really timely and very useful. I was really interested in the video that you showed and the hypothesis development. So like the LLM is kind of working through the thought process. Is that done iteratively with like a human, or is it like how does the human engage with
it? This is John. Actually, I get very excited when I talk about it because when we started as a group working on that, it was really, really interesting. So basically, the way it worked, so we use the Socratic reasoning. So the way that Socratic reasoning work is basically try to self-question the AI agent. It tried to make it more deep, because when we interact with the AI, sometimes we're not able to. So it basically tried to modify our question to be more, to be deeper scientifically, by questioning the AI. That's only for the question. And then we have the tree of thought, meaning like when we modify the question several times iteratively, then it basically generates several hypotheses. But we score the hypothesis. We do that based on our knowledge. So basically, we score based on our knowledge 1 to 3. And then based on that score, it's like a branch of the tree. It goes down and down to create our hypothesis. And we have a collaboration with AI agent, right? Because some of the things we know as because we have hands-on, right? We have
Right.
also knowledge which is different from AI. So this is how we collaborate with AI to generate the hypothesis
To
for
generate
our.
the hypothesis.
Yeah, this is really new, but I just wanted to kind of share it with you guys.
Yeah, yeah, very interesting. Yeah, thank you so much.
Absolutely.
We maybe have time for one last question if anybody has any burning questions.
Yes, this is Yang. So I work on electron microscopy, and unrelated questions for the AI agents. Did you use a existing LLM model, or is a new model trained by your own group?
For which one?
Like the one for hypothesis. Do you
I'm
use
sorry,
existing? Did you use a existing large language model such as ChatGPT or?
This is actually we are using the Gemini platform. Yeah.
Thank you. Yeah.
Maybe.
Sure.
All right. Any other last minute questions from anybody?
Doesn't look like it.
All right. Well, let's all thank Professor Ahmadi for a very interesting talk.
Thank you so much for the invitation.
Yes, it was lovely to